Good morning. Is this still okay? Need a little closer? Can't get it too much closer. This is the IEPG meeting at IETF 104. Again, if you're not at IETF 104, you're in the wrong room. It could still be fun. My name is Chris. That's Warren.
Have you turned it on surround?
Alternative facts.
No, it's not on surround, I don't think. Oh, it's just echoey. Okay. For the presenters, please stand on the pink thingy on the floor, X. Please, no dancing. Use the mic like this. Please don't use it like this. Okay, exactly. Very good. Okay, there are some presenters that sent slides, some that didn't. Perhaps they don't actually want to present. Here's the agenda. Okay. Is Stephen around yet? No, Mr. Farrell is not here. Okay. Simon, you're up. Oh, also, there's a pointy thing for the clicking and for the laser bits.
And monitor.
Yeah, monitor. Let me get your slides.
So, morning. My name is Simon Leinen. I work for Switch, which is the Swiss National Research and Education Network. I haven't been to IEPGs in a while. It's cool that so many people show up. Used to be smaller. Okay, and I'm here to tell you about buffers. There was sort of a plea for agenda items that were neither DNS nor BGP. So I try to fill that. I don't have nice slides, unfortunately, but I hope that I can interest you a little in this awesome, exciting topic of buffer sizes. So this is about sizes of the buffers in routers and switches. I think you probably all know why we need buffers. Internet is packet switched, and the flow control is mostly end-to-end, done by transport protocols such as TCP. And you need buffers to accommodate fluctuations in traffic rate and bursty traffic. You need them when you go from fast links to slow links, or when you aggregate many links at the same speed. But I don't have time to go into the details, but it's a huge space of situations where the buffer needs are very different. So how big should the buffers be? It's a slightly confusing picture. Many of us have sort of grown up with this historic recommendation that I think is also in an RFC 3000 something recommendations for link, what is it called? Link layer considerations or something. That is the work of Curtis Willemeiser and others on ANSNet in the early mid-90s, which ended up recommending to have buffer space in the router, at least the bottleneck router or switch, that corresponds to the overall end-to-end round-trip time, which is the average, I think, times the bottleneck bandwidth. So on today's networks, on wide area paths, that can result in quite big buffers. So this recommendation was, I think it's implemented by many people in the ISP space, certainly, though maybe not near the edges anymore. So in 2004, some people set out to challenge those rules, and most of them were around Nick McEwen's group at Stanford. And one of the early modifications to this recommendation claims that you can actually divide this buffer space rule by the square root of the number of parallel TCP flows that you have running across your bottleneck link. So that can be a big savings if you have hundreds of thousands of these or millions. but that was sort of put out there and researched and validated in simulations and so on. So question is, how does that translate into practice on the internet? There was some additional work to push this to even smaller buffers, making some trade-offs. For example, when you don't insist on being able to load the bottleneck link at 99.9999%, or when you can assume some pacing of the connections. I won't get into this. Anyway, this is quite a big spectrum of what we operators are told how we should dimension our buffers. So in practice, how big are the buffers in the switches? I'm looking specifically at these new commodity switching chipset like Broadcom or Mellanox or these kinds of things that are used by many vendors these days. Basically, there are two types. There are switching ASICs that have the memory on chip or maybe on package in the future. And those have very limited buffers. It's usually on the order of like 2-digit megabytes. I know some of the early ASICs had like 9, I think that's the least. And the biggest ones have around 64, if I'm not mistaken, of these on-chip buffers. And note that these switches have like 32 times 100 gig ports, so they have a lot of bandwidth, and usually they're deployed in places where people don't think the network is a bottleneck. But of course, due to things like incast or other situations that happen in the data center, that is not always true. And then there are chipsets, often very similar. For example, the Jericho chipsets from Broadcom, Dune, that can accommodate external memory for the buffers. And those switches have vastly bigger buffers. And the one reason is that you need a lot of bandwidth between the switching chipset and this memory, this external memory. So the chipset, I think a modern chipset uses something like 4 or so parallel GDDR5 connections between the chipset, the switching chipset, and the memory. So you need at least 4 channels of, or 4 sets of DIMMs, and the smallest DIMMs you get for memory are already quite big. So that's how you end up with much bigger buffer memory. But of course, there's a cost, because on the chipsets you need about half the pins and the SerDes or whatever external memory bandwidth of the chip. You now need them for this memory channel, and you can't use them for ports. So you get about half as much switching bandwidth if you do that. And also, building these systems is very hard. Building these channels to external memory, and yeah, there are MMUs, memory management units, on the switching chipset now that have to somehow accommodate the bandwidth and latency limitations of this memory. So it gets very tricky, and ASIC designers don't like that. They would rather build simple switches with on-chip memory, but the size is very limited. So of course, you may ask, why do I care? Yeah, if your buffers are too big, you're probably wasting money. And also there is the potential for like interfering with TCPs or whatever transports rate adaptation that is actually bad for performance. It will often be better to drop packets earlier. Well, I haven't put this on the slides, but we all know this. Queues, buffers should be managed actively, right? There's active queue management, which is also not widely deployed in the internet. I think it's, maybe there are some parallels to this discussions. If your buffers are too small, then you drop packets, of course. A burst may arrive at your buffer which doesn't fit, so you have to drop packets. This is okay because TCP is built on the assumption that the network will drop packets to tell me to slow down. But of course, the dropping of packets is often a bit unsensitive and can drop like innocent flows or flows that are just in a delicate phase of startup or something, and then that can lead to real performance limitations. Also, for distributed systems like you find in the cloud, people are often interested in these high percentiles, the so-called tail latency. I don't know, when you type a search query to Google, it sends it out to, I don't know, 1,000 servers, and you only get the results if like the last server has sent its response. Okay, this is not like this, but get the basic idea. So tail latency is important. And the big question I found in the discussion is that people optimize their networks, of course, for very different goals. And traditionally, when like 20 years ago or so, when WAN links were super expensive, people wanted to utilize them to the absolute maximum. Ideally, the links should all be running full at 100% all the time, and people should still buy my service. But of course, today, most people don't run their links full. Bandwidth has become a bit cheaper. It's become sort of an accepted approach to throw bandwidth at the performance problems. And the metrics, the metrics for which networks are optimized are quite different. For many of the cloud or content providers, the figure of merit is page load time, and page today is a very complex thing, of course, that can include many TCP connections and software interactions. Some people may be interested in low latencies if you do gaming or other interactive, I don't know, AR stuff or connected cars. So there's no consensus how you should build your network, because people build the network for different purposes. Of course, because we are the internet people, an ISP sort of has to be a bit agnostic of this. We have to build networks for just any application, and that picture always changes. So it's an interesting tussle space, I think. So one of the things I'm struggling with is that if we, like the research community, wants to encourage operators to sort of modify their thinking or experiment with new recommendations on buffer sizes, we have to give them the possibility to see how much they need, right? So I know about the ISPs in the room, whether any one of you thinks you have a good idea of how your buffers are used. I mean, it's not just for ISPs, also for cloud service providers or CDN operators or exchange point operators. I think exchange points are a particularly interesting case because they have even less control probably about what people send them as other people. So I found it a bit frustrating when I studied. I tried to study a bit for this problem that I found that even the commodity chipsets that are in all the products now, they have some instrumentation of what's going on in the buffers. Like Broadcom has some sort of high watermark recording, or where you can see, okay, in the last period or something, the buffer went up to this high. And Mellanox has a nice feature where you can actually split the buffer into slices of equal size, and the chipset would in the fast path would count how many times the buffer was encountered at the size range. I found that very nice. The frustrating thing is that the software we use on those switches doesn't allow me to look into this instrumentation, although it's there in the hardware. So that's a bit frustrating. In the past, also 20 years ago, I would have said, well, it's clear the IETF needs to define a MIB for accessing buffer statistics, because these days people don't necessarily implement this as MIBs anymore. But I think this whole story of how to give operators visibility into what their buffers are used for or how much they are used, that is quite quite interesting. I don't know whether someone in the IETF would like to work on that. Of course, it's not just how full your buffers are, although I think that is sort of the critical questions. You're running a network and someone tells you you don't need all this large buffers that you have. You really want to know, okay, how much of the buffers am I actually using, and how often, I don't know, maybe the average buffer utilization of my 4 GB buffer in my switch is only 32 kilobytes, but that doesn't tell me it's safe to reduce the buffers to, I don't know, 32 or a megabyte, because who knows how many times there will be peaks that go to 2 megabytes or something. But also, maybe not as much for ISPs, but you also want to know what kind of traffic, what flows occupy that space. That's a much harder problem to really look more into the structure of the stuff in the queues. I think that could be addressed. So either by some active measurements or this in situ measurements that also some switching ASIC people implement in their hardware, or by programmable forwarding planes. So some developments that might make it interesting to look at this problem again. I think it's, other than these modern chipsets and their design problems, and links always getting faster, that's not new. There are interesting approaches to limiting the queuing through the network both on transport protocols with things like data center TCP or other attempts at making TCP more, I don't know, more fluid-like, and limit some of these bursts. Some of this is going on here in the IETF. It's super promising. Yeah, and also there are people motivated to work on this again. So if I manage to interest you in the topic, which I hope, there's a few pointers here where you can look at everything that people studied over the last years. The reason I'm standing here is that 2-3 weeks ago there was a small workshop in Stanford also by the people who basically initiated this work like 12 years ago or so. And so they're willing to do more research with operators. There were a few very interesting presentations, which are not really online yet. I apologize for that. I need to hunt the organizers. I hope they will make them public. Should stop playing with this thing. So there was a lot of interesting content from operators of like content distribution networks, cloud networks, also some more traditional ISP people about measurements they did, for example, by artificially limiting the buffers in their switches, whether they got performance loss or even performance improvement in some cases, for the things that interested them, which were all different. And the workshop, the goal of the workshop was to organize a wider workshop for the wider community, maybe in fall 2019. So yeah, I'd say watch the space. I don't know what the space is, but if you're interested, then you could have the opportunity to talk more about this towards the end of the year. And of course, if you have ideas for measuring buffers, buffer utilization, impact on transport protocols, performance, and so on, then yeah, there are people interested in this. Certainly, Nick McCune groups. You can also contact me if you want pointers. So thanks a lot. That's all I have. Any opinions?
Hi, Jeff Howes. I am not an expert in transport, but I spend an awful lot of time looking at TCP. One of the things you should think about for the next version of this presentation is to include pointers to an older presentation that run through IETF on buffer bloat, because too much buffer, as you said, this causes problem. It's not the fact that the box has too much buffers, it's that TCP using that without any bounds tends to have really bad back pressure problems. So like you've mentioned, pacing of TCP is really what you're trying to optimize rather than burstiness. Second bit is speaking with the vendor hat on, measuring buffers in an abstract way for models is not going to work for you. The problem that you're going to run into is that for easy software-based systems, like say a Linux box or something like that, sure, you could actually get an easy exposure of those buffers and map that to resources used. But the minute you start actually getting to chipsets that have different types of buffer resources based on how it's trying to do different types of forwarding, you're going to find that you can't get a useful abstract model. You can, in existing modeling stuff like Yang, protobufs, et cetera, get nice modeling for what the resources are on the box. But even then, getting mapping to the resources to how they are utilized can be tricky. So like, pick on Broadcom as an example. They have a host table that has certain types of resources for fast hits to host level routes and different resources for everything else. So just simply getting that exposed can help in some circumstances, but even then you're down to one specific chipset for one specific line card for one specific implementation. So your visibility is only helpful if you're going to be running big data type analysis.
Yeah, thanks, Jeff. The buffer bloat thing is interesting because I see that as something where the community has made a lot of progress in a few years. So many of the problems have actually have progressed over the past years, which makes me hopeful for that the buffers are really, it's time to reconsider this. Well, in comparison, I mentioned this AQN story, which is sort of a sad story, I think, in our community, because there was a lot of research results and also some IETF work, and in the end, there's very little deployed practice. So, yeah, about the modeling, the difficulties of modeling buffer utilization, you're right. If you look into how the buffers are managed, it gets very complex, because also what I didn't mention, but these chipsets with many ports and like a blob of memory there, they have to allocate that memory to all the different traffic flows between ports, and that's very tricky. So the model it's hard to do the modeling. I agree, but at the moment I'm just frustrated that I can't look at all at these statistics that are being taken. So maybe even a bad model would be. I consider that as big progress. I don't know, maybe it confuses people, but...
Oh, so I'm not actually arguing there shouldn't even be any model. I'm just saying that don't try to push this through IETF unless you're looking for like a very broad abstraction on things, because you're going to end up with per vendor, per chipset. And the pressure that we're seeing as a vendor right now from some of our large customers, especially the data center guys, they want to see everything. The fact that you may want to shut off most of it in many cases is perfectly reasonable, because you want this information in many cases only when you're trying to troubleshoot things. So if you happen to know a specific line card is having issues, you can turn on monitoring for the resources, and that can give you useful information. You just realize that you're at a debugging stage and you're looking to see resources for a specific thing.
Jeff Houston, this is a really old topic, as you're well aware. I seem to recall one of the seminal pieces of work was actually Doug Comer back in the late 80s, where he had a 150 meg ATM switch with no buffer and managed to get a max of about 2 megabits per second out of it. And the consequent investigation as to what was going on. Part of this is the connection between the way TCP traditionally rate controls versus how switches work. And for most of our lives, we've worked on loss-based rate control mechanisms. I don't understand when a queue is building up until a queue is overflowed. When a queue is overflowed, i.e. the buffer is full and I'm dropping packets, I am going too fast. And then if you think about it, and a huge amount of work by Van Jacobson, by the time I get the loss signal, one RTT has gone past, I'm probably going faster. To what extent do I need to rate adapt in order to drain the buffer? And the crude mechanism that we came up with, which seems to have worked for the last 20 odd years, is ×2. So I rate half. And then I again slowly build up till effectively I'm filling up the buffers. When I get the signal, I rate halve again. That's meta-stable, and it probably needs to be because the world runs cubic. For that, you need big buffers. If you don't want to leave bandwidth on the table, you need buffers that are equal to the delay bandwidth product because of this halving property and doubling property. The real issue is actually work on BBR, which was old work on latency sensitivity that never quite worked. BBR has taken a different view, and it is possible to run BBR extremely fast with extremely small buffers because your signal is the formation of the buffer, not the overflow of the buffer. Now, if I was building chipsets, I'd be pushing BBR like crazy because all of a sudden I don't need large buffers if I've got TCP being latency sensitive. And if I was running large applications on today's network, I would use BBR. Hell, I am. Why? Because it knocks all those the loss-based systems off the table because they basically flood the network. So is there an evolution going on? Yes. Has loss-based systems, are they losing it? Yes. Why run cubic? I'm like, it just seems to be a totally self-defeating property when BBR, version 1 at any rate, version 2 got too polite. Version 1 just simply did it better with extremely small buffers, if that's where you were.
Yeah, it's an interesting evolution or just a
Janai Iyengar, thanks for that talk. I was actually going to step up and say something quite similar to what Jeff said in terms of the interaction between the congestion controller and the queue management system. Ultimately, what we're talking about here is not simply buffer management in the network, but the whole system of sender congestion control or rate control and how buffers are managed in the network and what those signals of drop/ECN mean to the endpoints. So whoever wants to look at this problem, I'd strongly encourage them to look at the entire system. Now, coming to the entire system and congestion controllers, Jeff is right that BBR does a better job of managing the buffers, but I would push back gently against the fact that BBR does not actually kill cubic. It's super important to say that. Well, I want to look at those traces for sure because it can. There are certain conditions under which that can happen, and as he pointed out, BBR v2, which if you're interested in, will be presented at ICCRG this week, and you're welcome to talk to the people who are working on it now there. Will be friendlier, is my understanding. I haven't actually seen exactly what's happened over the past several months there. But in general, the congestion controller, not just BBR, a better congestion controller is something that we want. So to reduce the buffer bloat / buffer management problem, with the two sides of this are basically going to be how do you do good AQM and how do you do good congestion control. I don't think BBR is the final answer in this, but I think that's in the right direction.
Thanks.
Sorry. Is Steven in the room? No. Yana, you're up. Nope. Let me just find your slides again.
I just moved from one mic to the other. Well, thank you for waking up early and showing up to this talk, to this session. This is a much bigger and more crowded room than I anticipated. But I'm going to try and stand here so I don't block that view there. My name is Janai Iyengar. I work at Fastly, and I am an editor in the Quick working group, and I am here to talk to you about Quick observability. How many of you have wondered what to do with Quick once it gets deployed in your network? Well, a handful of people, not bad. So let's talk about it. I'm not going to be able to answer all your questions. I'm not going to be able to give you all the bits, but I'm going to tell you what the current state of affairs is, and then the floor is open. You can come, beat me after that. Thank you. So what are we talking about? For people who've been under a rock for the past 3 years, people who've been under a rock for the past 20 years, that's the HTTP stack. For people who've been under a rock for the past 3 years, that's what Quick replaces. So Quick is basically replacing all of TCP. It doesn't replace TLS, but it subsumes TLS. It doesn't subsume TLS. TLS sits inside of Quick in a slightly strange way. And then there's a new HTTP that's being built to run on top of Quick, and that's HTTP 3. So the surface that's exposed to applications on top will remain the same, but HTTP 3 is basically the HTTP mapping over Quick. TLS 1.3 sits in this strange way right there because it's basically Quick uses TLS as it does in the other stack, as HTTP does in the other stack, but Quick uses TLS to do the exchange, and then when the keys come out, Quick uses the keys to encrypt its own headers in addition to application data. So as compared to the previous stack where only application data was encrypted and the transport headers were visible in the network, in the Quick world, the transport headers are also encrypted and not visible in the network, most of them anyways. So those are the drafts. If you enjoy reading drafts, those are available. Before I move on, one of the most important problems that Quick, there are several problems that Quick set out to solve, but the most relevant one to this conversation is the one around middle boxes. Presumably, everybody's familiar with this here in this room, so I won't go into the details of what exactly I'm talking about here, but the problem that we're trying to solve is that of ossification, is that we have been unable to change TCP in quite a while. You've seen TCP fast open, you've seen MPTCP, a number of extensions to TCP come out of this community. How many people would claim that if you put a probe in the network today, you would see a TCP fast open SYN? Are you claiming that you would see TCP fast open SYNs if you put a probe in the network?
Yes.
It must be in your private network because there isn't very much out in the internet.
No.
Yes, that was my point. Sorry. I didn't make it very well.
That can be your alternative path.
Yeah, go ahead, use a mic.
Hi, Jared
Yes.
Mauch. Yes, I do see some of these. Thank you.
I would love to talk to you more later.
Thanks. I do run a global backbone, so yes, you can talk to an operator about the implications that Quick has for operators, because that doesn't seem to be a piece of the consideration as that was considered as part of the working group.
It was, and this is not what I'm here to litigate. I'm here to
No.
talk about the tooling that's available for Quick. We've had this discussion ad infinitum, but in general, right now, TCP fast open, I've tried to deploy it, I'm unable to deploy it. And if you see TCP fast open packets on the wire, I'd love to see what fraction of TCP is actually using TCP fast open, because that's a number that we're actually interested in, to be clear. And I'm interested in it. I've been pushing for TCP fast open for quite a while. And it's super difficult to deploy. Apple's found it hard to deploy. Microsoft's found it hard to deploy. Google's found it hard to deploy. And it's not because we've not been trying. We've tried, and middle boxes still break it in various insidious ways, and we're unable to deploy it.
So what I'll comment on is that originally when ECN was implemented, there were certainly a lot of boxes, these middle boxes, that did go and black hole connections that had the ECN bit set when TCP was set up to initially do that. And being an early adopter of some of these technologies, I've absolutely seen the types of behaviors that you've documented as part of this, and that you're using, that you're listing up here on the slides to saying, yes, these have caused me operational problems in the past, is the fact that people have non-standard devices deployed in the internet. Some of the ways to solve that isn't necessarily always to create a new standard or to create a new protocol or a new method. Sometimes you have to go and do what, for example, Mark Andrews over here has done with trying to do stuff with the DNS protocols, where he goes and he's taken the time, he's researched, he's identified which TLDs, CCTLDs, et cetera, that are not compliant with the standards, publishing the list, publishing the research, and going and actually doing the work. to actually go and clean up some of these devices, as opposed to saying, fixing these is too hard.
So
I'd
let
like
me-
to just make a new protocol instead.
I'll let you have the last word on that point, and you did. I'm going to move on because we're not going to relitigate this point here. The point here is that this was one of the core motivations for why we did develop Quick, and it is deployed. And it has it's taken less than 9 years to try and see any bits on the wire. So it's a strategy that has worked. So one of the arguments I'm going to make, and this probably plays into the point that you just heard, is this. So a while ago, Google's version of Quick, which is called G-Quick, has been deployed for a while now. But then this is a few years ago, and Google's version was deployed, and this is before Fastly I was at Google, and the first byte of this packet header was the flags byte, and you all know what a flags byte means, right? A flags byte means it has bits that you use, you turn on and turn off. We decided to flip a bit, and because we wanted to change a particular behavior, we wanted the header to change a bit. We changed, and this is before Quick was even published as an IETF draft. It's before any of this had happened publicly, but Google Quick was deployed in Chrome, and this was unencrypted, and we had left it at 7 for a while, and we flipped a bit, and everything went to hell. Basically, we had calls coming in going, users can't reach Google over any Google property using Chrome. And by the way, this is Chrome's problem because guess what? We can using Firefox, right? And so we had to go find out where the problem was. We did. We found it was in using Quick that this problem showed up. Long story short, this was basically a firewall that we found deployed in enterprise networks that allowed the first packet in both directions to go through, which meant that Chrome basically had I'm going to try, like a happy eyeballs, like I'm going to try Quick. If it doesn't work, I'll fall back to TCP. And the doesn't work was concluded based on whether the handshake packet came back or not. So Chrome would send out a handshake packet. This firewall would let it through. The response would come back from the server. The firewall would let it through. And then when Chrome decided Quick's working, the firewall would black hole everything. So this was exactly like the perfect mismatch between these two mechanisms, of course. And we spoke to the firewall vendor. We spoke to them in detail about exactly what had happened. And we actually spoke to the team that implemented the code that did this. And they said that the way they determined what quick traffic was, they wanted to ship a feature that did quick blocking. And the way they determined what quick was is they looked at TCP dump for a little while and found that the first byte was unchanging. And the way they implemented a filter for quick was basically this. So I'm not going to make too fine a point here, except to note that the one byte that didn't change on the wire ended up becoming the quick identifier. And I will say this for what it's worth, we still don't know what's going to happen when we change this byte tomorrow. Right now, the Google Quick that's deployed doesn't have 7, it has 9 in the first byte. That is the bit we flipped, by the way. The second bit is the bit we flipped. It is 9 right now. So I don't know if this has changed to equals 7 or equals 9, or if it's changed to something broader. So we have to see what happens next. However, this was a pretty strong reinforcement of something we already knew, that the only way we could actually protect a protocol from getting completely ossified, and for us to be able to deploy without having to wait for 10 years as we waited with TCP fast open, was to encrypt. Yes.
So this is a great story, Aaron Falk, Akamai. But basically, if I understand what you're saying, is that you were running a protocol on the network that was not published anywhere, and so somebody used a heuristic to figure out what it was.
Yeah,
what else could they have done?
So it's a fair point. So with a couple of things they could have done. One is, so it was published as a public document. It wasn't a standard. I should have said that clearly. The document was available, but they hadn't even looked at it. I mean, they hadn't even Googled Quick. To be very clear, when we asked them, they had no idea the document even existed. And then they asked us, the next time you make a change, can you please let us know? And we said no. So we don't know what happened after that. But yeah, that was the state of affairs. Yeah. But if you want to ship a feature, I would expect that there be some amount of due diligence. It's not to put, I'm not putting them on the spot. They're probably serving their business purpose adequately well to continue to survive and exist, right? And to thrive even. It's a big company. But incentives are different in different places. And they aren't incentivized to go look up the spec. That's a pretty strong signal to us. We can write specs all we want, but we have to figure out how to incentivize these folks to go look at the specs. So at any rate, this was a lesson that was reinforced. So what's the status of this work? We've been working at the IETF for the past 2 years on standardizing this, on working on this 2.5 years now. And everybody understands that there are obviously privacy and security implications, as well as network operational and management concerns. And it's unfair to say that those haven't been considered. Those have been absolutely considered. It's just that I think that the community is worn down by the inability to move transport or end-to-end bits, and we are trying really hard to figure out how to make this work. This means that there might be fundamental changes in how operational work happens going in the future. I don't think that should be off the table, and I think that that sort of work is encouraged now. So we've had a very strong focus on avoiding ossification, because we want to paper over the network that as it is, and we want to avoid middle boxes looking at the headers. If there are strong reasons why middle boxes need to get some information, there's a very high bar for how to demonstrate that. And that has to be a demonstrated need. And I think that is critical. I think that should have been established 25 years ago. Unfortunately, we didn't have the experience that we have now. So as an operator, if you're thinking, what can I do here? I would recommend that you think about what exactly you need. And the working group will be open to have a discussion on that. So there are several implementation efforts. How much time do I have left?
Probably about 5 minutes for questions.
5 minutes for questions. I actually wanted to go into the packet header, but I'm not going to go into the details here. I'm just going to show you, and I wanted to show you some tooling here. The packet header basically has two flavors. There's the long header and the short header format. The long header format looks like this. It's only used for the handshake. It's only used during the handshake to bootstrap, to set up the connection. And the bits you see there, which are not marked out with XXXX, are visible in the network. Those are unencrypted bits visible in the network. In the long header. When you get to the short header, actually, that's not a great picture, because I'm not going to say, this doesn't show you everything that's encrypted, because the packet number here is encrypted. But only some bits are actually visible. And I'll actually show the short header is the common header. That's what's used during the rest of the connection after the handshake is complete. And this has a bit here called the spin bit that you may have heard of. And if you haven't heard of it, you've again been under a rock for the past 2 years. Climb out of there. But the spin bit is basically a bit that is available in the short header, and it's meant to be used for passive measurement of round trip time. I won't get into the details of how, but that's visible in the network, and that's available for the network to use to measure round trip time. Folks at Ericsson and other places are doing a ton of work on figuring out how to use this, how to build filters and tools around this, and so on. Again, that was a very strong case that they had to make, that this was super useful and super important bit of information in the network, and that eventually came out of that discussion. A very heated one, I'd say. So that's the packet header. If people who are familiar with TCP might say, I can see a packet number that looks like a sequence number. Where's the acknowledgement information? Where's the flow control information? Well, as it turns out, none of it is in the packet header. They're all inside the packet. So a packet basically is constituted by frames, and you can have different frames. There are many different frames, of which there's the stream frame that carries application data and the ACK frame that carries acknowledgement information. I'm not going to just throw a whole bunch of information out at you here, but I'm going to skip these and show you basically what a quick packet looks like. There's the packet header. The grayed out bits are ones that are encrypted. So the packet number is in fact encrypted. You can't see the sequence number on the wire anymore. And pretty much everything else inside the packet, which is the stream data, the acknowledgement information, is all encrypted. So clearly, Wireshark is not going to be enough because it really can't see very much without having an endpoint key. And that's how that's going to be with Wireshark. You're not going to be able to get a lot of information. But there's been a lot of tooling work that's going on for doing endpoint tracing of Quick. And that's seen a lot of traction. So if you're a server-side network, or if you're a client-side network, then there's a bunch of tooling that work's been going into. And if I may just very quickly show these two bits, QuickTrace and QuickWiz, are two tools that have been under serious development, and they are very, very promising tools. The first one, QuickTrace, written by Victor at Google, is available. It's open source, and basically is a packet trace that shows you, like if you've seen TCP trace or other tools, it's quite similar to that. It shows you a time. It's basically a time sequence diagram of packets and ACKs and losses and things such as that. QuickWiz is a much more elaborate tool being written by Robin Marks at University of Hasselt. And this shows some seriously interesting information that you can get from doing stuff, logging at the endpoints. These are all available to see at, these will be discussed in much more detail at the TSV area session this week. So there's a half-an-hour talk on QuickTrace, a half-an-hour talk on QuickWiz. So if you're interested in these, please show up there. And I think we have maybe a minute or two for questions.
Excellent. Hi, Jared Mach still.
Hi.
So I have I think an important question, which is, what are you doing in the protocol? You've taken so you've gone and you've moved from protocol number 6 to protocol number 17, and gone and encapsulated your data within protocol 17. And a number of global network operators have deployed Proto 17 rate limits, and sometimes Proto 17 rate limits with ephemeral port numbers in them. How has the Quick working group consulted with those operators about what the consequences are for the protocol in detecting ephemeral port, either black holes or rate limits? And I can give you some history if you'd like.
So I can speak to my operational experience at Google with this, which is that when we deployed Quick at first, we found about 93% reachability with Quick. So in terms of black holing, that may have been the 7% that we missed. And that was perfectly fine because we had a TCP fallback. So if Quick didn't work, that was perfectly fine. The rate limiting is the more nefarious one because
I'm sorry, how is like rate limiting a denial of service attack?
I didn't say it's a denial of service. It's the more nefarious one.
Yeah. Well, that's why the rate limits were deployed.
I think we're talking past each other. Yeah. Were you going to say something, Chris?
I think you're both talking about the other side of the problem. Like he says the nefarious one, meaning suddenly my packets are weirdly not getting there. And it's really hard to figure out why, versus your side of like, somebody's trying to DOS attack my customer, clearly I'm going to rate limit that.
Right.
Yeah,
I think that's exactly what it is.
Or I'm going to rate limit attacks that traverse or are against my network infrastructure.
Sure.
Because I don't want to have to carry attack traffic to another continent, for example, which I think is a legitimate operational use case.
I think that's completely fair, and I'd love to talk to those people. If you have those people,
if you'd like, you could talk to me.
And I think
talk to Job from NTT, who's also publicly said that he's done this. There's also a number of other global networks that have done this as well, that have published this in the operator community. So I'm kind of curious where this disconnect is between the Quick working group and the operator community who are deploying these things.
So the discussion has to happen in the Quick working group by the operator community.
So they have to come to the IETF?
Well, they have to come somewhere. I don't know exactly what.
The Quick working group could.
I don't think this is a productive conversation here between you and me. What I can say is that operationally, our experience at Google was that when we turned on Quick globally, and right now, to be clear, Quick is about 40-ish% of Google's traffic. Last count, it was 40% 2.5 years ago. And that's about 7% of internet traffic. So I'm sure that you're seeing quick packets right now flowing over the networks. Rate limiting was something that was observed. It was definitely observed. And what we did was we cold called operators. And most of them were in enterprise networks. And they basically said, we didn't even know that we had a rate limit on. We got 3% back just from doing that.
That's good.
So yeah, we did get people to turn off the throttling because those are on by default in their firewalls, not because they had turned it on. We still have we mostly have gotten rid of the rate limiting at this point. The most recent data was from last year, which shows that most of the rate limiting that Google sees has gone down. It doesn't exist at this point. It's quite possible that it's still happening in corners that I haven't seen or heard about. But if it's happening in a big way, then it's certainly missing Google's traffic.
Okay, yeah, I mean, I've tried to bring this to people in the Quick Working Group, and they have not been listening. And so that's why when you've come here this has more operators in it, and that's why I'm trying to reinforce this message that has not been heard.
Right, so I very much appreciate that. What I would say is that
so my second question is actually more about why as other protocols are moving away from UDP, such as DNS, and they're moving
How is it moving away from UDP?
Yes.
Hang on. If you're talking about DOE, you're talking about DNS or
No.
HTTPS.
Thank you. You have confirmed my point.
All right, I'm clear. I am sure you have a point to make, but you didn't make it to
I'm pretty sure I
me.
know which working group has the disconnect based on this conversation.
So to be very clear, I'm not the working group. I'm here doing a presentation about quick tooling. This is, I think, the reason the conversation is breaking down is because if you want to have a conversation with the quick working group, you need to talk to the chairs. Get a slot, discussions made. I'm not representing the working group here. I'm representing the discussion I'm having. I don't think this is a productive conversation at this point here. Weston.
Hi, Jeff Oz, who is not Jared. Since this is operational considerations, and I haven't been following Quick in the specs for a while, what's in the specs right now for the fact that we're using UDP and this impacts ECMP for forwarding?
You could still do ECMP with the 4 people. I mean, it's sitting it's in UDP.
Well, so part of the point is, and your slides sort of approach this a different way. Leave my packets alone, the contents are secret. Routers have to actually find some level of entropy within the packet to actually hash stuff.
Sure.
And trouble with UDP is most boxes that are actually doing ECMP on UDP have a limited number of entropy that they'll actually do. They don't tend to peek into the contents of things. They try to stick mostly to the headers. So one of the considerations therefore becomes the quick specs should talk about ECMP only goes this level of deep, and be very careful how you actually do your flows on this, because otherwise you're going to find that despite the fact you have massive fan out for your ECMP, especially in data center situations, if you're not careful about how you play with your port numbers, your traffic all smashes down the same port.
Sure.
And you two guys up front obviously know this because we've had long conversations about this sort of thing. But for your presentation here, this is an important thing for the rest of the people in this room.
Sure. So I would say that ECMP is still usable, and a lot of deployments actually do use ECMP and are planning to use ECMP for sharding traffic, for quick traffic coming in. But there is, if you're willing to build in the support for it, there is a connection ID that is in fact visible on the wire, and that's at a fixed point in the packet header. That can be used for sharding, and that can be as long as 17 bytes. So you can certainly use that for sharding as well.
Right. And again, the point becomes, at some point you have to figure out, how do I look into the packet in a safe fashion? And this comes back to, is the spec stable enough so that ASIC implementers can actually do this?
That's a fair question, and I think the draft is approaching. It's basically more or less approach stability right now, and yeah.
Right, but so if this is not in the specs, it's worth getting them added. Let's figure out who needs to have that conversation.
Last question.
Eric Klein. So given that everything is now hidden, of which I am a fan, one performance enhancing proxy that does strike me as having been useful is the things that are like the TCP TCP munging for satellite links.
Hmm.
Are you aware of any measurements or experience of how Quick behaves over satellite links?
No, but I don't expect it to be any different than TCP over end-to-end satellite links.
It just won't have any in-network assistance. It'll have to
That's
discover
It just won't.
characteristics itself.
Yeah. So at the moment, that's a conversation that we can and we need to have going forward. But it's something that at the moment, if this is again why we expect that. I mean, HTTP, for example, every single implementation of it is probably going to will have a TCP fallback. So ultimately, if you need those devices, then that's the way to get those performance benefits out.
Well, but I mean, if you were operating a satellite network, you'd want to provide all protocols that the end user might want to
Yeah.
use with whatever their best experience could be. Do you think in-protocol mechanisms within Quick for learning this are satisfactory?
Do I think the protocol mechanisms that are in Quick right now are satisfactory for not for this purpose? They're not going to be adequate.
They're not.
No, they're not going to be adequate. I think
Thanks.
we need more support than this. Me?
Both of you.
Oh.
Really? Okay. Well, I thought I was eating the mic. The question was
Not
about
enough.
satellite links and Quick performance over satellite links. But
Yeah, I mean, so not a lot of work has been done in there. There's probably, congestion control and other work. The protocol doesn't offer additional hooks for things like that to happen at the moment. But it's certainly possible to imagine that next revision of the protocol might have more things to support other network types.
thank you.
Aaron Falk, just a point of information on that last topic, that there's a mailing list called ETSAT that's discussing performance over satellite links, including with Quick, so for folks who are interested.
Thank you for that.
Okay, is there a Stephen Farrell in the room? Nope. Job, you're up.
Catch.
Good morning, IEPG. Can you hear me properly in the back of the room? I will talk louder. This is really awkward. My name is Job Snyders. I work for Entity Communications, a IP transit provider. And in this presentation, I would like to discuss some ideas or considerations related to BGP blackholing. Quick recap what blackholing is. Blackholing in general is that you signal to an adjacent network, usually your transit provider, please do not send me packets destined to this IP address. And the common use case is that you receive, say, a DDoS attack targeted towards one of the IP addresses originating from your network, and you sort of disable this IP address in order to allow the other IP addresses to remain reachable. In other words, you're sacrificing the victim of a DDoS attack so that the rest of your services remain online. Fine. Usually, blackholing is implemented through one of two methods. One is what I call in-band signaling, where on the BGP session with your transit provider, you announce a host route with a special BGP community, and that special BGP community triggers the blackholing behavior. Or a second approach is out-of-band signaling, where you have a eBGP multi-hop session towards a special route server in the provider's network, and that route server will inject a black hole into the ISP's network. When you receive a black hole request, the big trick is that you rewrite the next hop to an IP address that is null routed, or you rewrite it directly to the null interface. Now, the downsides of this approach is that your request to not signal, to not receive traffic for a given IP address also becomes the best path if it passes through the filters, because your request is conflated with also being the most specific route to a given destination. Another downside is that on most BGP implementations, you will need two filters. one filter to catch the black holes and figure out which ones you would want to allow. And the other filter is for normal BGP routing. To put this in perspective, today's largest config in NTT's network is 57 megabytes, and roughly 50% of that is because of black hole related prefix lists. Now, most providers will use IRR or RPKI or WHOIS data to construct these filters. And we've noticed that some of our customers either maliciously or accidentally have requested black holing for IP addresses that are not theirs. We've seen customers that would add ASNs of their competitors to their own AS set, so they make it into the filters, and then they signal black holes into our network. Of course, this upsets some customers. We've also seen accidents where a DDoS mitigation system misidentifies a DDoS flow, and it starts blackholing for IP addresses that are outside that customer's network. In any regard, all of these situations should be proactively prevented rather than reactively, where we disable blackholing capabilities for such customers. This is an example routing policy. You can see we have two lists, one for black holes, one for normal routing. If the destination that we receive over the eBGP session is in the black hole list and the community is our black hole community, then set a specific next hop and jump out of the policy. If that conditional requirement is not met, it may be a normal routing signal, and then we would accept it. Now, my proposal to this community is that we should only honor black holes if they align with the active path. So if you're receiving traffic for a destination, then you should be allowed to signal black holes. If you're not receiving the traffic anyway, for instance, because you're not the best path, your AS path is longer, then your request for blackholing should at that point in time not be honored. So what I propose is a black hole validation procedure. For instance, if I receive a black hole on a certain edge router, and I also have a copy of the RIP, the local RIP of that edge router, I can walk the RIP and see if the next less specific route is also pointing to the same next hop, or if the next less specific route has the same ASN in the leftmost position of the AS path. There's a number of ways where you can validate, is the black hole request aligned with the best path? Whichever method you pick, I think this will bring significant benefits to your other customers. Now, the implication of only honoring black holes if you are the best path are numerous. For instance, it makes it much harder for networks to black hole traffic of their competitors, because their competitors are maybe directly connected to your backbone and have the shortest AS path or a higher local preference. This trick where we make black hole validation depend on the next less specific route also causes us to enjoy the benefits of any type of filtering we do at our edges, like bogon filtering or RPKI origin validation or IRR-based filtering. In other words, you have to put in effort to become the best path. For instance, you'll be announcing a /24, which is the longest that will propagate in the DFC. And then, in other words, if you want to black hole with this method, you will have to combine a black hole request and a BGP hijack in order for the traffic to disappear. And that is a significant higher barrier than what we see in today's black holing implementations. So in black holing reconsidered, I think there is multiple input channels or listener channels that we can consider. You could give an API key to each customer and let them post the requests to a certain HTTPS endpoint. We can use in-band BGP signaling, where we either use BMP adjacent RIP in pre-policy to catch these requests for black holes, or use a trick where you don't install the received black hole routes into your FIP and only export those routes to a special BGP validator, not to any other iBGP neighbors. Or we can use out-of-band signaling through eBGP multi-hop sessions, where through an MD5 key you can assure that you are talking to your customer. In this new world, we can remove the black hole policy related to the /32s. We only need to install prefix list filters for normal routing. If we see the community and a specific prefix length, the actions that would follow would be to advertise this route to the black hole validation server, do not install in FIP, and exit the policy. So I really expect up to 50% reduction in our router config size, which is really nice. Our plans at this point in time, we're within the PM-ACCT project, are working on a black hole validator implementation. This will be open source software, free to use for everybody. PM-ACCT is a very powerful toolkit that already has a lot of the moving parts, such as BMP or BGP capabilities. It can already walk the RIP in various directions and perform comparisons between more specific and less specific routes. And if the request would pass the validation step in PM-ACCT, then PM-ACCT will emit an action into a stateful database, such as Redis, and that data stored can be used to generate injections into your network. Because in all these components, you want to be able to reboot the edge router, reboot the validator, reboot the injectors, all the while we need to be able to maintain the state of these black holes. A cute trick is that this can be implemented on virtually every BGP implementation, as long as they support either best external path advertising, or you do your injection through an ACL or some other means. I think there's many ways to skin this avocado, but the good news is that everybody gets to has an opportunity to implement this in their network, and we don't need to wait for vendors to support us. What I also like about this approach is that it goes very well with RPKI origin validation. In this community, RPKI origin validation and black hole have been considered a problematic situation, because we don't want people to create ROAS that allow up to /32, because that opens you up to certain attack vectors. This means that black hole route announcements are almost always invalid announcements and should be rejected. But by using this validation step, and depending on a less specific route, we can use RPKI origin validation on the normal routes, and those will pave the way for the black hole records to be validated or not. In other words, RPKI origin validation and validated black holing work very well together. This is a community effort. At this moment in time, NTT Communications and Telia Carrier are working towards implementing this method in their networks. And PM-ACCT is the validation software. And we hope that in May, we'll have something to publish and for others to work with. So the summary of this presentation is, unlike the traditional way of implementing black holes, I posit that black holes should only be honored if they align with the best active path. If you're not the active path, we will ignore your black hole request. And with that, I would like to open up the microphone for questions, comments, and considerations.
Rodrigo von Deutsche Telekom. I have been looking for something like making sure that I only honor the black hole when it goes the same path as an active route. And I'm certainly going to look into how the mechanism actually applies. I have one nasty p-counter comment on the presentation. I really hate to see the opening sentence, black holing is signaling, which it obviously is not. In the signaling, you are carrying requests, and in parts of a presentation, you were talking about the requests. I personally like to speak precisely and really distinguish between what happens to the packets and what's happening in the signaling. The other thing is my requirements for security and following that authorization for the black holing probably are a little bit higher than can be achieved by the whole setup that you are discussing. But, well, okay, what you are discussing quite clearly is a big improvement over what is used by most people today.
If I may address your second comment. By making the black hole requests dependent on the normal routes, and with normal, I mean what passes through our filters, what I'm suggesting is we can make the filters as strict as we can, and maybe you have a different policy than I have, but the point is that anything we do for normal routing will positively impact the black hole feature. So if we deploy origin validation, the black hole signals or requests become of higher quality. If we apply bogon filters or filter out ASNs that we should never see behind that eBGP session, what I'm saying is the better the quality of our normal prefix filters, the better the quality of our black hole requests.
Completely agreed. That was essentially my first comment, that yes, this improves stuff. Well, okay, the last comment is, well, okay, actually looking at the nasty details, the authorization requirements that I'm using today are in certain ways more strict than what you are doing and what most people are doing. Even you're pointing to using origin validation. I think if I start to look at the nasty details, in my opinion, I will end up opening up black holing to be started by parties that, in my opinion, are, well, okay, where I do not have the authorization by the address holder that I should be accepting the signal from that third party that is somewhere in the path.
Yep. If you are an IP transit provider like NTT or DT, and you want to talk more details how to implement this in your network or how to plan for this, please talk to me or email me. If you're a vendor of BGP software, please recycle some of your flow spec validation code so that we can do this validation trick on the box rather than off the box. And I fully understand that this will take 2 or 3 years to hit the mainstream customer releases. That's fine. Until that time, we can use the PMACCT black hole validator. But ideally, I would like this to be on box rather than off box. Any other questions, comments? Thank you for your time.
Is there a Steven in the room? Okay, Fernando, it's you.
Yep, this and this. Just put this right here so we don't push it off the mistake. Yep. And on the plus sign right
Okay, so I'm Fernando Gont. I'll be presenting essentially a document we co-author with Young Source. Sorry? It's better? Okay. That was discussed mostly on the 6-man and B6Ops mailing list. The reason for presenting it in this meeting is obviously because we'd like your feedback and your ideas. Sorry. So there we go. So if you have been following the 6-man and the B6Ops mailing list, well, this document triggered quite a lot of discussion. There were essentially like almost 300 or over 300 messages that were triggered by this document. This document discusses an operational problem that arises in some renumbering scenarios. Actually, the problem had been pointed out before in this ID by Jan Linkova, and it was actually to some extent discussed in a right document, 500 something, the document about recommendations about prefix sizes. Okay. So there are multiple scenarios that can actually lead to this problem. We are just going to focus on on the most simple one. This is obviously a very common deployment scenario for IPv6, where you have the CPE router that is doing DHCP prefix delegation with the ISP, and you get a prefix list, and then you advertise on the local network a sub-prefix from the prefix that you were list, right? So that's quite common. Now the question here is, before we get to the problem, this I covered. And something to keep in mind, which is quite important for the problem being discussed, is some of the associated parameters, with this deployment scenario. On one hand, typically the router lifetime that is advertised on the local network is in the order of over 30 minutes. Typically, if I remember correctly, the default value is 30 minutes. And the list time is normally in the order of several days to months. Okay, so this is essentially the problem that you might experience. Let's say, for example, that the CPE is hard reboot or it crashes and reboots. It could also be the case that the user, I don't know if that's common in let's say in your environments, but we are quite used to whenever you have a problem with your internet connectivity, even if you call the ISP support, usually the first way to solve the problem is like, have you tried resetting the home router? So those are among the reasons that might lead to this scenario. So the question is, what happens when, for example, you reboot the CPE router or it just crashes and reboots? Well, quite normally, these devices, they don't keep any state regarding the prefix that had been previously listed. So normally they will do the HCP prefix delegation again, and depending on the policy of the ISP, they might actually get list a new prefix. Okay. Now what happens is that, of course, they get list a new prefix. They will advertise a sub prefix on the local network, but the question is, what happens with the previous prefix? Okay, so you got a new prefix, you advertise the new prefix, but nobody told the network that the prefix that had been announced before has actually become stale. Okay, so essentially the old addresses are maintained. Quite frequently, the old addresses are preferred, and obviously also the old routes are preferred, meaning the old prefixes are considered on link, and the addresses that you had configured before are still preferred. So you keep the old addresses and you configure additional addresses. Now, what's the problem with this? Of course, the previous addresses have become stale. So if you try to use them, they will fail. This means that, for example, B6 connectivity might fail. Or, for example, if you are using, let's say, a browser that implements happy eyeballs, well, B6 connectivity would fail and you might end up preferring IPv4. Okay? Let's talk about a couple of deployments that might avoid this problem. So the approach that was recommended in the right document, I don't remember the name of the document off the top of my head, is to use stable prefixes for networks. Okay. Well, there are pros and cons. For example, it's nice for law enforcement because if the user always get the same prefix, it's easier to to track the user. On the other hand, it's not nice for privacy because even if you do, for example, temporary addresses, well, that's kind of like in vain because you change the interface ID, but the prefix is always the same. So you can be tracked with a prefix. Some ISPs report that they provisioning systems, they don't allow them to do this. And also there's the case, whether you agree or not, that some ISPs want to change extra for stable prefixes. I'm not saying that should be the case, but that's something that happens. So that means that by default, they give you a dynamic prefix, because if you want a stable prefix, you have to pay extra. So the bottom line of this is that it's quite normal to actually get dynamic prefixes. There was some kind of like survey that had been performed on this topic. I don't remember the numbers, but I think it was something between 25 and 35% of the surveyed ISPs that were leasing dynamic prefixes. So in the case of those ISPs that had been surveyed, in around 25% they were using dynamic prefixes, meaning that you might potentially hit this problem. As a personal point of view, I don't think that the solution to this problem should be to use stable prefixes. Or to put it in another way, I mean, even if you don't, the network should be resilient and still not break if the ISP is listing dynamic prefixes. Then there is another deployment, let's say, scenario, if you want, that might help avoid this problem, which is the case in which the CPE router actually records the prefix that has been listed on stable storage. Okay, so the idea is that when you do DHCP prefix delegation, you store the prefix that you have been listed on stable storage. So in the event of a reboot, you might do DHCP prefix delegation again. And if you learn a different prefix, what you might do is advertise the old prefix with a lifetime of 0, like preferred lifetime and valid lifetime of 0. Okay, kind of like you advertise the new prefix with the normal lifetimes, and at the same time you advertise the stale prefix with, let's say, 0 lifetime, so you can somehow disable it or deprecate the prefix. Now there are a number of problems, or this is kind of like tricky. First of all, if you look at RFC 4861, it says that if prefix information option has a valid lifetime smaller or shorter than 2 hours, the valid lifetime should be ignored. So that means that even if the CPE router tried to deprecate the prefix, the old addresses will, couldn't actually be deprecated. You can unprefer the prefix. So the preferred lifetime will be honored, but not the valid lifetime. And in any case, there are many of these boxes that just don't record the least prefix on stable storage. So that means that that's not something that happens in practice.
Richard Battison, that's right out. You kind of corrected yourself there. So we can use the preferred lifetime of 0 to deprecate it. It's deprecation versus invalidating. So that does work. So
yeah,
what's the problem?
No, so in that case, if the CPE was recording the prefix on stable storage, which doesn't need to be the case, but in those cases in which that happens, then you can advertise the prefix with a preferred lifetime of 0, but you wouldn't be able to communicate with the new owner of the prefix. Why? Because you still have configured the addresses. So for example, that prefix will be considered on link.
Yep.
So if you want to, let's say, communicate with the new owner of the prefix, it won't be possible. Now, there is another problem that is not mentioned here, that some implementations enforce limits on the number of addresses that they can configure, okay? I don't remember if it was Linux. They, I think, enforce a limit on 16 addresses, okay, from different prefixes. So if you consider that the default valid lifetime for a prefix information option is of about 1 month, and you assume that the implementation limits the number of configure addresses to 16, then if there is like a reboot of, let's say, every day or every other day, you will actually hit the limit. So even, if you were to do this, when you advertise the new prefix, since you keep the old addresses, since the old addresses are still maintained, eventually you will hit the, the system limit on the number of prefixes for which you configure addresses. So that of keeping the old addresses doesn't come for free, okay? Now, besides, the fact that, CPE routers could do something along these lines, unfortunately, this is something that you cannot rely on to, right? Because, well, there are deployed boxes that they just don't, record the least prefix on stable storage. So this is our take, of course. This is something that has been proposed on the mailing list and is something that we have considered. One of the proposals was to actually try to somehow affect the source address selection algorithm. For example, one of the things that was proposed is that you should always make the address with the largest preferred lifetime the preferred one, okay? So that's one option, which doesn't actually make sense because, it's up to the each prefix which preferred lifetime is employed. And another option that is better than option one, which doesn't make sense, is to essentially associate a timer which with each prefix that is advertised on the network, like a timer that or a timestamp, actually better, more proper word, a timestamp that essentially indicates when was the last time that the prefix was advertised. Now, if you were to use, for example, as the preferred address, the one that was last advertised, then you could say that in a scenario in which your CPE router crashes and reboots, well, the stale prefix will not be advertised anymore. So a new prefix will be advertised, and then you would use the correct address if you want. Now, there are a couple of problems related to this. First one is what I mentioned in the previous slide, meaning that you wouldn't be able to communicate with the new owner of the prefix. That's one of the problems. Second problem is that since you keep the old addresses configured, you might hit the system limit on the number of configured addresses. So meaning if you get, like, for example, one reboot every day, after a couple of weeks, you will have configured 16 addresses and the new prefixes advertised will be ignored. So that's a problem. Now, there is another problem, probably not as bad as this one, which is if you are in a network segment where there are it's a multi-prefix network, so two prefixes are being advertised, let's say by two different routers, then as these two routers advertise their corresponding prefixes, the source address of your packets will flap, okay? This router says a router advertisement, so this prefix was the last one being advertised, so you start preferring this address. Then the other router advertises a different prefix. Now you start sourcing packets from that other addresses, and it's guaranteed that the source address of the packets will flap. Okay, that's kind of like not nice for troubleshooting. There are a number of things that we think could be done to actually, let's say, solve or improve the situation with respect to this problem. Let's say the most important mitigation from our perspective is essentially to do something along these lines. I mean, there are multiple ways in which you could possibly implement this, but essentially it goes as follows. If you are receiving RA packets from the same router that had advertised your previous prefix, and the RA contains prefix information options, but not the previous prefix for which you had configured addresses, well, that should be taken as an indication that the prefix is stale, okay? So what we do essentially is, for example, we wait for two arrays from the same router that contains prefix information options, and after the second one, we unprefer the address, and after two additional ones, we actually completely remove the address and the onlink route, okay? It's kind of like tricky and hacky in the way that, in theory, the prefix information options don't need to be contained all in the same array packet. So yeah, in theory, you could say, you know, there's a router that is advertising, let's say, 3 different prefixes, and it sends 1 different array for each of the prefixes. Yes. I haven't seen this in practice, okay? Let's say the good part of this is that you can essentially solve the problem on the host side without actually requiring any changes on the network devices themselves. So that means as soon as, you know, you implement this, let's say, mechanism, then no matter what, you know, whether the ISP is listening stable prefixes or not, or whether the CPE router, you know, records the prefix on stable storage or not, you kind of like overcome the problem. Now, really, when you know when we were you know, analyzing this problem, we started to, let's say, rethink or reconsider some things related to Slack and neighbor discovery. So, first one, for example, normally the prefix lifetime in prefix information option by default is of about 1 month. Okay. Now the router lifetime is 30 minutes. Now our question is, you know, to what extent it makes sense for the prefix lifetime to be larger than the router lifetime. If you think about this in the context of RFC 8028, which is about, you know, multi-prefix networks, it essentially says that when on any given network you have multiple prefixes, well, the prefix should kind of like be tied to the router that advertised the prefix. Why? Because if not, if you start sourcing packets, you know, from one of the prefixes that was advertised on the local network, and you send those packets to the wrong router, well, it's quite likely that they are going to be egress filtered. So normally, what you want is to source packets from a, you know, from a given prefix only towards the router that actually advertised that prefix. In which case, I don't know to what extent it makes sense to have the prefix lifetime larger than the router lifetime. When we were discussing this topic with a number of folks, the only reason that, let's say, we found for this is that in the event you have an outage with the ISP, then you might continue using this prefix. Now, from my perspective, I kind of like differ a little bit with that. So what I would say is, and of course this, I'm not saying that this is probably acceptable to most people, but probably if what you want is it's like a prefix that that you can actually use irrespective of what happens the ISP, that might be an indication of what ULAs are for. That's one thing. The second thing is that what you could have is that the local router never advertises the prefix with a lifetime larger than the router lifetime. So even, you know, even if communication with the ISP is lost, well, the local router can still continue advertising the prefix, okay, for as long as the prefix lifetime. So in that sense, for example, if one were to cap the, you know, the maximum value that one honors for the prefix lifetime, let's say one could limit, you know, the amount of time that this breakage lasts on the network. I don't know if there are comments or questions.
Eric Klein, you and I spoke about this stuff before. One thing that just came to mind was, I think actually the easiest thing to do would be for the host to do some kind of bi-directional forwarding testing. By basically try to send to an address in the PIO, send an originator packet to the router that the router should write back to it.
Could you repeat?
Bidirectional forwarding detection, BFD. There's several RFDs about BFD. If there was a host-based BFD where you would just basically send the packet to an address that you yourself already have, but emit it, you know, send it to the router's MAC address, the router should bounce it back to you. If it doesn't, then your PIO might be gone.
Okay.
After a couple of those BFD probes, then you can say, yeah, the PIO is really gone.
Which is the address that you'd use as a destination for that?
One you have already configured.
Let's say you have an address configured for the prefix. Okay, you want to check that that's working. What's the destination address that you use for the check?
The same. Or configure a second one. It's Slack. Configure 17 addresses and do BFD probes between them.
So you
As
said,
long as you're listening to the ND messages, you've subscribed to the solicited node multicast group. The router should be able to find you and send the packet back to you, or issue a redirect.
so the source and the destination would be the same. You send the packet to the router and it comes back to you.
This is a lot about how BFD works. So I think this would be actually the best solution. It would solve a number of problems as well.
Janinko, first of all, I think you need to clarify on your slides for people who might not be following the whole story, is that all this router behavior is clear violation of RFC when it does not record the previously assigned prefix, right? So we're talking about definitely broken router implementations, not something which is expected as per standard, right? So what we're trying to fix broken routers, misconfigured routers, packet loss, and so on, right? We're not talking about situations when everything works as per RFC. Secondly, I do not think that flapping source address is a bad thing if you have multiple prefixes on the interface. It's already happening now if you're using longest prefix match, right? So if my host has two addresses on the interface from two prefixes, you don't know which one will be chosen for the next connection. So it's already happening. So it's okay if your host start selecting a random prefix for a source address. And actually, it might be desirable if I'm advertising two prefixes from two routers. I might actually see kind of load balancing there. So that's fine.
What do you say that the source address would be the same if you applied the source address selection algorithm? Why would it lead to a different outcome?
No, what I'm saying is every time my host opens a new connection, right, it will apply default selection, source address selection algorithm. And even now, without proposing use the most recently updated address, you don't know which one will be used for next connection. It will be random depending on your destination, because the longest prefix match is used.
No, but I agree with that. But given the same destination, nowadays you always get the same source address. Now, if you modify the source address selection algorithm, given the same destination, now the source address would change. So now you try it and it works, and you try it later, you just get a different source address and it doesn't. So for troubleshooting, that's not nice.
I would say if you have privacy extension, it might actually still get different source addresses, but
same prefix.
Well, I think actually, I personally, in my network, I would love to see hosts doing kind of load balancing that way. It would be nice. So it might be actually desirable behavior, but again, back to the proposed solution. I think, first of all, we definitely need to tweak the timers because the current standard default timers do not make any sense. But I'm still not convinced that we need to significantly change the logic of the protocol to work around broken routers. I think the proposed changes to heavy and drastically change the whole logic of evidence of absence is not absence of evidence is not evidence of absence when you should not make any assumptions based on information which does not present in array.
One thing that was proposed, I don't know if it was Eric that had proposed that, is, for example, if the previous prefix is missing, one thing that you might want to do is send an RS to the router, like poll the router and see if the prefix is there. That's one option. The thing is, somehow you need to get rid of the stale addresses. So what we
reducing prefix preferred lifetime will do what you want, right?
Sorry?
Basically, reduced preferred lifetime and make it more in line with the router lifetime.
Yeah.
Do most of the trick for you.
But still, you keep the old addresses, and if you get multiple reboots during the month, you will hit the system limit. For example, I don't remember if
you also make valid lifetime like slightly bigger than preferred lifetime. It doesn't have to be months, right? It can be a day, for example, right? So you do not keep those addresses for a really long time.
So under which circumstances you will reduce the valid lifetime?
So basically, your preferred lifetime should be X, and your valid lifetime should be, 10 times X, but it should not be a month. That's what I'm saying.
So you're saying that when the prefix is advertised, the valid lifetime should be smaller?
Yes.
I agree with that.
All timers should be smaller because current timers don't make sense.
As a side comment, when I was trying to track, what was the reason for which we had the timers that we have, I ended up talking, because, normally you get these values over time and, and people get used to them and there's supposed to be like a reason for them, but nobody knows what the reason is. And I talked to the one of the original authors of Neighbor Discovery, and what he mentioned was that, for example, for the router lifetime that has a default value of 30 minutes, was because at the time there was the idea of using IPv6 to communicating with the moon. So the router lifetime had to do with that. Now, we got used to that value, but when you think about the reason for which that value is there, it's...
Jafaz, so BFD is probably the wrong tool here. BFD is very good about telling you something's gone down very quickly. It's less intended for, are you there? Are you still alive? No. So coming up test, not so good. Going down test, very good. There is something called seamless BFD that's a little bit better than that for unsolicited cases, but then the router advertisements would have to actually carry a piece of BFD info in there. What I'd suggest is that ping is probably actually a better check for a lot of these things, just to simply check to see if stuff's alive. It's
ping
there.
Against whom?
ICMP.
By which address would you be pinging?
The exact same thing you attach your BFD sessions to. So yeah. So and the only reason I even got up to the microphone is we've had people in IEEE land and other places want to use BFD type procedures, didn't like actually using BFD machinery, and then still called it BFD anyway. And I just want to not see this happen inside IETF as well. Ping works perfectly fine. No, some basically you're looking for some sort of loopback test. That's really all you're looking for. It's just being able to source route packets from a host through the router and make sure that you can actually get the answer back.
What would happen if for some reason they were filtered?
Well, that's if it's filtered, then you have a different problem.
Well, Windows does filter ICMPs, as far as I remember. So.
Yeah. Well, to some extent, the conversation about the lifetimes of your networks, part of the thing I'm not seeing in this conversation is network partitions. Now, if you're in a real organization, like an enterprise or something like that, you expect that network partitions are going to be small. For the most part, if they're happening, you want things to fall apart as fast as possible. That's what routing's for. But when you're looking at this stuff being used like in a home environment, people walking in and out of Wi-Fi range, plugging in and out of stuff. Somebody accidentally plugged in, some Apple equipment that knocked over things because spanning tree was broken. Pick your favorite bug class of things, but partitions happen in network environments for houses all the time. When you start looking at other cases where you might want to use IPv6, where extremely low power networks, packet loss heavy environments, when you have those types of partitions, a stable address becomes very important. So the ULA type scenario is actually a good solution for those things, but I'm not a V6 expert. I dip my toes in occasionally, and ULA doesn't seem to be working well in a lot of environments or well deployed in a way that it seems to solve these problems. A lot of cases, link locals in a network that is actually properly put together would solve exactly the same solution, but too many devices need to be in the middle of these cases. So you do want long lifetimes just to have stable addresses. Trouble is, is it ULA? Is it the globally assigned one for your router? It doesn't matter. It has to actually have a long lifetime.
Eric Nygren, this is certainly anecdotally I've seen being a real problem in the world, and where it seems to happen is kind of the combinations of not great implementations across a bunch of areas. So if you have a not great implementation of a client application that doesn't do happy eyeballs, and a not great OS that might be running a 10-year-old Linux or some very old Linux kernel that has basic IPv6 support, and a network device that or a home router that is doesn't have the best implementation, that combination together can, combined with like the ISP's practices, can result in some fraction of users being in a network being broken like this. And what I've seen is that if that ends up being a few percent of users running some smart TV with a IPv6 app that doesn't do happy eyeballs on a old prefix, is enough to cause major content providers like national streaming services to get enough user complaints coming in of, oh, hey, my users can't stream stuff. They end up switching content back to IPv4 only. So it's a real problem. And ideally, because of that nature of how this happens when a bunch of things are broken, looking at how many of the, what are simple fixes that people are unlikely to get wrong in ways that make it worse on each level of those steps are probably maybe one of the better ways of like encouraging apps to have better happy eyeball style fallback behavior, doing something on the OS side and doing something on the router side that are each simple, because that may make it such that if you fix at least one of those things in the chain, you're less likely to have these sorts of problems.
I have another crazy idea for you. So I assume your solution relies on the host tracking prefix to next hop mapping, right? Prefix to next hop. So basically it should be 8026 compliant, right?
Yeah.
So yes, we basically do not care about old hosts in this case. What if, again, as an additional mechanism, you suggest that router use a new link local for every new prefix generated? In this case, your host will always prefer the active link local, which corresponds to the actual active prefix.
I'm thinking out loud. How would a prefix advertised by a new link local would become preferred over the
because you have two next hops now, right? And one of them is not reachable anymore because the prefix is gone.
It is reachable. The router
No.
itself.
If your router doesn't have that prefix anymore, it doesn't have a local address anymore, which means that particular link local will not be reachable.
Okay.
And network reachability detection will tell host that this should not be used, so it will be selecting maybe it will be selecting the right next hop. It's actually, I'm just thinking about it. It might be something to consider.
Yeah, I think
it's kind of MPVD stuff, right?
Yeah, I think there are two things to consider here. One is, for example, if you could take as much time as needed to solve the problem, how you do things. On the other hand, the question is, well, what could you do, to actually solve the problem without having to wait for that long? Because, for example, in that case, in order for the problem to be avoided, then you need each CPU router to be updated. Whereas with the mechanism that we are proposing, as soon as the host, implements the behavior, the problem is solved.
So I think we need to implement a number of things which make the whole system more robust. It doesn't have to be one thing.
Yeah. I agree with that.
So we can consider different things which make the solution better. It doesn't necessarily be one.
Yeah.
Right. So maybe in some we can talk which one, as has been mentioned, could be easier to implement in terms of what people can get wrong there.
Yeah.
And what other things we can deploy without actually, again, introducing too much complexity and tweaking the logic of the protocol too much.
Yeah, I agree. I think that's it. So thank you.
Okay. Unless there's a Stephen Farrell in the room, we're all done. Stephen? We're all done. That's it. Thank you very much. See you next time.